What kind of things can light do? Well, we have emission, absorption, transmission, reflection, refraction, diffraction, absorption, interference, polarization. We've got stimulated emission. We've got Fraunhofer diffraction. We've got the photoelectric effect. We've got total internal reflection. These are all capabilities, things that can happen to electromagnetic radiation. I'm going to start by describing emission. Emission is when light is produced by an object. And there's basically three ways that I know of that light can be produced by an object. One of them is called thermal emission. This is kind of the light that, for instance, that's produced by the sun. The sun is called a 5,000 Kelvin black body. And the reason it's called a black body is not because it's actually black, but because if it was exposed to radiation, it would absorb it. None of the light that you see coming from the sun is coming from reflection. It's all coming from the internal heat of the sun. And that's just like any black object is not producing it's not reflecting any light. Now, what about spectroscopic emission? Well, first, I should mention something about refraction before I go on, but one way you can identify whether something is spectroscopic or a black body radiation is by sending it through some refraction and getting, which usually separates out the different frequencies of light into bands. You can also get this same effect out of a diffraction grating, except the diffraction grating is going to split it into bands on two sides. But when you send a spectroscopic emission through a diffraction grating or a prism, you'll get something like this. You won't get a continuous rainbow pattern, but you'll get specific lines that are coming out. And the lines that come out are based on what elements are present in the star. It's basically the element present is producing specific frequencies of light based on exactly what orbitals its electrons in and how much energy it takes to go from one orbital to another. And the third type of emission I talked about was metallic. Maybe a better word for this would be like radio transmission, or I've got this word here that's I'm not sure how to use. I kind of think maybe transmission should be used here, but transmission could just mean any kind of passage of light through space. On the other hand, they have like transmission towers. Of course, these transmission towers look to be all power line transmission. What I'm looking for is more like this thing. Wait, maybe? Yeah, this is more like what I'm looking for. Something that will send out radio waves, but is not sending them out as a black body spectrum or because of quantum mechanical effects inside the molecules. Rather, they're going to send out FM or VHF or AM, whatever kind of frequencies that they need to broadcast. That's the word I'm looking for. Put broadcast emission there. Now, for each of these emission methods, there is also an absorption method. You can have thermal absorption. When you stand next to the fire, you will feel the heat of the fire, or the electromagnetic waves from the fire being absorbed right into your body. Or when you're out in the sun, you'll get the same thing. Spectroscopic, of course, if a photon hits a atom in its ground state, it will interact with the electron and push it up to an excited state. That is another way of absorbing spectroscopic light, or absorbing light spectroscopically. Also, the energy can be absorbed by the photoelectric effect, where not only does the photon go up to an excited state, it gets pushed all the way outside of the atom, where it can be used as a current. That is where the electron will be available and decrease the resistance of the material, because it's available for flowing across longer distances. Speaking of electrons flowing freely, let's discuss metal and conduction bands. The valence band. Alright, these diagrams don't do that good of a job of showing this, but I found this really good animation of the effect. Basically, this guy has got a switch here, and this shows atoms inside the metal. The electrons are more or less free to move around as they please, but when he turns on the voltage, the electrons start moving through pretty quick. Resistance, I guess, comes from just bouncing off the atoms for the most part. He's even got, what's that called? Showing the electrons kind of moving, bouncing off random objects. It's called it's a phenomenon usually known as Brownian Motion, where basically these particles are bouncing off unseen molecules in the air. The main point I'm making is once you have a mostly metallic body where you've got a lot of free electrons, then you can start making those electrons work in concert to produce electromagnetic waves, and you can do broadcasting and receiving with them, so that emission and absorption kind of looks like broadcasting and watching things on TV. So let's move on to reflection, because there's two types of reflection. One of them is called specular reflection, and the other one is called diffuse reflection. Almost everything you look at in the world is caused by diffuse reflection. You're not seeing any emitted radiation from most surfaces that you look like. The rare counterexamples are light bulbs and the sun. For the most part, you're seeing diffuse reflection of objects, and then there are rare counterexamples of that. When you see specular reflection, you're looking at a mirror. Next thing I think I would like to talk about is refraction. Refraction occurs because the speed of light in different transparent substances is different. So the speed of light in air, for instance, is greater than the speed of light in glass. Now, the way I like to visualize this is that the photons have a size, like little cars driving along, and when the car hits this interface, its left tire is going to hit the glass first, and so at that time the right tire is going to start to overtake the left tire and cause the car to turn slightly to the left. You can also think of this in terms of a marching band, where the guy on the left starts to run into the mud, and so the people on the right will overtake him, causing them to turn until everybody is inside the glass, and then they can continue movement straight forward. Now then, in general, this phenomenon takes different effects for different colors. For instance, the speed of light for purple light in air will be greater than the speed of light in glass for purple light, but I'm going to put a much greater than sign because it's going to have a greater effect for purple light than it does for red light. For red light, it's only a little bit more, and so it will end up turning the purple light more than it turns the red light, and you'll end up getting a rainbow effect. Next, I'm going to start talking about interference effects, because interference effects include diffraction and Fraunhofer Diffraction. They also include something called two-slit interference. And what interference does, if I have a light bulb over here and it's producing light waves that come out in circles, and it hits right here, and it will produce a continuing circle, and it hits right there, it produces a continuing circle. What's going to happen is that the peaks of these waves are going to interact with the troughs of the other wave, like right there, and create basically no light, while the peaks of this wave are going to meet the peaks of this wave and produce a light spot. And so what you'll get on a screen in the distance is a bright spot in the center, and then another bright spot, bright spot, bright spot, bright spot. And here's kind of what a one or a two slit interference pattern would look like. It's got this big bright spot in the middle, and then the bright spots off to the side are about half the width as the big one in the center. Now you can also get, besides getting two slit interference, you can actually get an interference pattern from just one slit. And this is called Fraunhofer Diffraction. And it comes into play quite a bit when you're discussing a maximum resolution of telescopes. This is one of the big reasons that they make large diameter lenses. Because what happens is that each point of the object will, instead of creating a point on the film, ends up creating, instead of a point, it creates this diffraction pattern. So the size of this diffraction pattern kind of limits the resolution of any image created by your telescope. Now the mini slit diffraction pattern we've already seen. It comes out pretty similar to what a prism does, mainly because this phenomenon here, where these waves are interfering and constructively and destructively, is highly wavelength dependent. So you will have one wavelength interfering constructively at one place on the screen, and another wavelength interfering constructively at another point on the screen right next to it. So it's really kind of amazing that these two devices, the prism and the diffraction grating, can produce such similar results by such completely different methods. So what did we have? We already covered absorption, that was listed above. I'll mention total internal reflection right now. Total internal reflection can only happen when the light is trying to move from the slow to the fast medium. So you got your little marching band here coming in, and when he comes down here, he's going to speed up while this guy comes down. But if he speeds up enough, he ends up going just straight that way, and at a certain point in there, right at that point, is called something called the critical angle, and you end up, instead of transmitting through the fast speed of light substance, you end up just reflecting back into the slow speed of light substance. Here's a laser going through a stream of water that is totally internally reflecting. So this is kind of how fiber optics work. So next, I guess last thing I'm going to talk about, resonance and photoelectric effect, and what I call H-bar, which is written H with a bar through it. The photoelectric effect is a process, I think I described a little bit of it earlier. Basically apply a voltage to a surface, and then it doesn't produce any current, so until you shine light on it, and it doesn't matter how much light you produce, it won't produce any current unless you start to use a light of a high enough frequency, and then suddenly the thing will start to produce a current, because there's free electrons in there that can be moved. Now most people use this as an argument for the idea that that light is a particle. I'm not entirely sure I agree. I kind of think this is more an example of some kind of resonance effect, or maybe it's just a matter of you have an E field. Each photon has a certain electric field associated with it that's moving along, and that electric field is based not on the number of photons. Okay, and that's sometimes why I make these videos, because I'm about to argue myself into a corner. If I have a large number of photons coming in, then the electric field of those photons should combine and create a larger electric field. But instead, we have all those photons coming in, and doesn't matter how many of them there are, we need a single photon that will produce a large enough electric field to to pull apart to pull the electron out of the atom. But I think it's also a good idea to look for an explanation, although I haven't found it, based on resonance, that somehow the frequency of the atom and the frequency of the light has to match somehow in order to get it to respond. And I also want to bring up the h-bar phenomenon. H-bar is one version of Planck's constant. Now Planck is an interesting figure in physics. He's the counterexample of physics people that I kind of want to follow, because Planck was over 60 years old when he made most of his headlines. Most people these days say that your chance of becoming a famous physicist is reduced greatly by the time you turn 20. But I never really wanted to work that fast. When I was 20, I was too busy listening to The Cure and playing Dungeons and Dragons. But wow, that got off topic. Anyway, Planck's constant is basically the quantum level of angular momentum that is generally, I believe, is what separates the orbital shells of a hydrogen atom, at least. And this is one of those things that I'm kind of uncertain of, but I'm going to repeat until I see until I can correct myself anyway. Basically, the electrons run around in an atom with quantized energy, angular momentum levels of 1 h-bar, 2 h-bar, 3 h-bar, etc. Is what I would call an equipartition of momentum at discrete levels of angular momentum of h-bar. So when an electron comes in, or when a photon comes in, if it is not high enough to apply this amount of angular momentum to the atom, if it doesn't have that kind of torque to spin it out, then the atom will either reflect it or just transmit it. It won't absorb it. It doesn't matter how many atoms you have that are bigger than that. It's just not going to work unless you have a single photon coming in and hitting it and making it bounce. Alright, the last thing on this list is stimulated emission, and then this question, does a photon have a size, which I'm going to leave open for now. But stimulated emission is what happens inside a laser. And I don't know exactly how it works, but let's see what they say in How Stuff Works. And you'll see they start us out with the basics of an atom, and how an atom will absorb an electron by sending an electron into an outer orbit. So in a laser, you've got this lasing medium, which is usually a gas, I think, of some kind of phosphorescent type of material. And very intense flashes of light or electrical discharges pump the lasing medium and create a large collection of excited state atoms. So this is the stimulation part. The atoms are excited to a level that is 2 or 3 levels above the ground state, and you get this condition that's known as population inversion, which means there's actually more atoms in the excited state than there is in the ground state. Now the main thing that the laser produces that other lights don't is coherent light. I think that has to do somehow they're able to open up the aperture for such a short period of time that all of the light that is hitting the aperture at that time is somehow aligned so that the peaks of the waves and the troughs of the waves are all aligned. The key to a laser is a pair of mirrors, and the mirror at one end of the laser is half silvered, so it reflects some light and lets some light through. The light that makes it through is the laser light. So I guess there isn't any process that actually does, I don't know what creates the coherence, because I would think that the half-silvered would need to be timed somehow to only allow the waves to come out at a certain time. But I did remember that I did not discuss polarization yet. Most light that you see is not polarized. It just has one particular, or it has many different directions that the electric field is going. But if you polarize it, all of the light will come through with the electric field being aligned in the same direction, and the magnetic field basically being aligned opposite of that, perpendicular to that. So,
you might be wondering, is light a transverse or a longitudinal wave? It's designed to let waves get through. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through.
okay, well that covers almost everything that I can think of that light does. And for the most part, the next few chapters are going to be about describing some of these things in more detail.